Hi everyone. So today I have a very interesting concept for you, and that's called rotation of a curve. So we're gonna see how rotation of a curve works out when you rotate that particular curve by an angle theta. And yes, without wasting any time, let's get started. So this is a question from the Stanford Math Tournament in the year 2021. And in this video, we're going to be looking at the rotation of a curve by an angle theta, how exactly that pans out. Then we're going to be looking at point of intersection of two curves, which is really a very simple technique, but it's quite useful. Then we have some book suggestions for senior math Olympiads, and at the end, a simulable challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
So what are they trying to tell us? So the function y is equal to x squared does not include the point 5 comma 0. I think that's pretty obvious, right? It includes the point 5 comma 25, but not 5 comma 0. Okay. So let theta be the absolute value. So theta is positive of the smallest angle the curve needs to be rotated around the origin so that it includes 5 comma 0, and then find the tangent of that angle. So to kind of simplify this down, what they're trying to tell us is that we have this curve y is equal to x squared, standard parabola. And obviously, it does not pass through this point 5 comma 0. And that's pretty clear, yeah? But they want us to rotate this curve by an angle, let's say theta, such that it does pass through 5 comma 0. So when you rotate this curve by an angle theta, they're trying to say that it will pass through 5 comma 0. So it looks something like this, for instance. Right? This is 5 comma 0. So it will essentially pass through x equal to 5 once you rotate it by this angle theta, and then essentially find the tangent of that theta, find tan theta. So I think essentially what the question should be is that what exactly do we mean by rotation of a curve? Like, what exactly is this happening when I'm rotating by an angle theta? Like, what exactly is it happening? And I think you kind of get the intuition that, for example, if this is, let's say, the curve, when you rotate this by an angle theta, what will happen? So try and visualize this with me. It will form some sort of a circle, right? It will form like some kind of a circular manner, something like this when you do like rotate it. I'm doing a very rough figure, but it will form something like a circle. And if it's hard for you to visualize how the curve will kind of transfer, you can just analyze one point. How will this point shift when you're rotating it by an angle theta? It'll go here, 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 here, and that is how it will complete the 360-degree transformation. So you're rotating an angle theta, and theta can obviously vary between 0 to 2 pi radians, right? Or 0 to 360 degree. So whenever you're rotating this, just imagine this particular point. You can take any point. I'm just considering this because I think it's easy to visualize it from that point. And when you rotate it, and I'm considering a clockwise rotation. Now by convention, theta is positive when it is anti-clockwise, and it's a negative angle when it is clockwise rotation, but that's just a convention, doesn't really matter. So when I rotate this, let's say in this manner, so you can kind of like see the curve being rotated, and at the end of it all, the curve is essentially tracing a circle, or this point is tracing a circle when it is being rotated by that angle theta. Okay, great. So how does it kind of relate to our point? Well, let me just draw this again. We're just playing with graphs essentially. It's very interesting. So this, okay, great. So, and then we have obviously this circle, and this circle needs to pass from 5 comma 0 because you're rotating it through theta and you want it to pass through 5 comma 0. That's what the question. It has to pass through 5 comma 0. You're taking the angle theta such that this curve y is equal to x squared is passing through 5 comma 0 when rotated, right? So let this point be, I'm just going to like name a point. This point, let it be P with coordinates obviously x comma y. We don't know that yet. And if you cannot get the idea, this px comma y is the point of intersection of this curve and this circle. So what are we essentially doing? So we are rotating, just write it out maybe. So we are rotating the parabola, or we are rotating the curve y is equal to x squared, and once you rotate it to an angle theta, point P becomes phi comma 0. So you see point P is on this curve. If you just forget the circle for a moment, point P is effectively on the curve, and once you rotate that curve, this point P will eventually become phi comma 0 after a little bit of rotation by an angle theta, right? And the origin is a fixed point, right? I think that's a critical thing as well. The origin is a fixed point, so therefore the movement is like a circle, right? Which we kind of visualize up top as well. So again, just to kind of recap, whenever you want to like visualize how a curve transforms after rotation by an angle theta, you can just consider this particular point and then just imagine the trajectory of that point. It'll be like rotating like this, right? And it will like eventually form a circle once you consider all angles theta from 0 to 360. Okay, great. So what next? So I think the forward step would be to maybe try and find this point P, right? So we need to like find this point P. So find P, right? Find P of x comma y. Try to find the coordinates of this point. What exactly is this point? Try to gain some kind of knowledge about it. But what is P? P is essentially the point of intersection of this curve and this circle, right? P is basically point of intersection of curve and circle, which is essentially the trajectory of the curve. Now, what is the equation of the curve? Y is equal to x squared, which is given in the question. What's the equation of the circle? Now, the circle is centered at 0, 0. I think that's pretty clear. Origin. And it has a radius of 5 units, because it needs to pass through 5, 0. So, equation of a circle that is centered at 0, 0 and radius is 5. What's the equation of such a circle? Well, we know that equation of a circle is x squared plus y squared r squared. Again, just keep in mind that this is only for a circle centered at 0, 0. In general, we can write x minus h whole square plus y minus k whole square is equal to r square, where h comma k is the center of the circle, right? Is the center of the circle. And in this case, h is 0 and k is 0 because the center is the origin. So this then becomes x square plus y square to r square. In our case, r is 5. So x square plus y square is equal to 5 square, which is 25. So x square plus y square is equal to 5 square, 25, and y is equal to x square. And we need to find p of x comma y. So p of x comma y is basically the point of intersection of this curve and the circle. Or if you look at it in the diagram, it's this point. It's kind of the point of intersection between this curve, y is equal to x square, and the circle. So therefore, it must satisfy the equations of both the circle and the curve, right? So what you do is just you plug in y is equal to x square in the first equation. And when you plug in y is equal to x square in the first equation, you get an equation in which you only have terms of x. So x square plus x is power 4 is equal to 25, and this can be very easily solved. Just take x square is equal to t. So this becomes t square plus t minus 25 is equal to 0. And then we just use the quadratic formula. So t is minus p plus or minus square root of 101 by 2. But we know that t is equal to x square, and x square is always greater than or equal to 0. And therefore t must also be greater than or equal to 0. So we just ignore this negative. So t then just becomes negative 1 plus square root 101 by 2. The negative just gets ignored. Okay, great. But since t is x square is negative 1 plus root 101 by 2. Or in other words, x simply becomes the square root of negative 1 plus root 101 over root 2. I should probably include that inside. Negative 1 plus root 101 by 2. Okay, great. So now we've kind of found out this point, this point p, right? P is what? X comma y. And once you found out what x, y is nothing but x squared. So you can find out y as well. And I think that's really interesting because now the problem is essentially solved. To kind of just remind you what the diagram looked like. This was a curve, y is equal to x squared. And we had this kind of like a circle. yeah, which obviously passed through the point 5 comma 0. This was at angle theta, and this was P x comma y. So if you just analyze this point P x comma y, don't you think it's kind of forming like a triangle? Where this is y, this is x, this is obviously theta. Or if you want to see it over here, you can think of it like this in a way. Where this is indeed a right angle triangle. Right? That is how it would look like in the figure. But like this, what I've drawn over here is kind of like an enlarged version of that. So tangent of theta, what we need to find is nothing but y over x. What is y, guys? Y is x squared. This is y and this is x. Right? So what is y essentially? Y is x squared. So tan theta then becomes x squared by x. So tan theta then becomes x. We do know the value of x, and that is why we needed to find this point P. That's why it was so critical to find P, because we know the value of x. And just plug this in. So tan theta just becomes x. And what's the value of x? X was this, I believe, root of -1 plus root 1 over 1 by 2. So theta then just becomes tangent inverse square root of -1 plus root 1 over 1 by 2. We just had to find tan theta, but okay, I'm finding theta. This is approximately 64.8 degree, which can be again approximated as 1.1313 radians. So I think that's a pretty interesting question. We learned how we can kind of rotate a curve and angle theta, and I think it's very simple actually. It's not very complicated. You just kind of need to visualize how the curve will move in a way. And in our case, it was very simple. You could very clearly see that it was a circle. And then you just found the point of intersection and use some basic trigonometry to find out this tangent of theta. So yeah, I really hope you learned something from that. Okay, so moving on, we have certain book sessions for senior math Olympiads. I am a compendium, polynomials by Barbeo, elementary number theory by Sierpinski, graph theory by Harari, combinatorics by Brualdi, secrets and inequalities, functional equations and how to solve them by Christopher G. Small. Okay, so we have a similar but challenging problem. And here we don't really have a curve, but we rather have like a figure, a closed figure, convex figure. And it says that the rectangles with given vertices is rotated clockwise through the point 2, 0, then about 5, 0, then about 7, 0, and finally about 10, 0. Okay, so again, this is kind of like playing with graphs. Just graph this out and then just see how this clockwise rotations happen, right? And then it's saying the point initially at 1, 1 traces a curve, find the area of that curve. So like we're kind of analyzing the trajectory of that one particular point in the parabola in our question. We then need to analyze that. It's kind of like the same thing for the point 1, 1, which traces a curve, and find the area of that curve. So we try this out, and if you're able to make any progress on it, or if you're able to solve it, let me know in the comment section. Until then, I'll see you in the next video. Thank you very much, and bye-bye.
The programs are designed for students who are passionate about mathematics. And they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.